Okay, don't forget we have a quiz again at the beginning of this lab coming up this week. This will be a little more difficult than the element quiz. You are going to be looking at what's called polyatomic ions. Poly means what? Many. Atomic is going to obviously be in reference to atoms. So polyatomic many atoms. These are ions. We're getting ready to discuss ions, but these are ions that exist where there are multiple atoms that make them up. And I'll clarify this as we go along, but for right now, some of these things, they're just going to have to be some memorization is what's going to happen here. I can't, if there was a way to teach this, then I would, but this is the reason that I have a separate quiz for this. You're just going to have to memorize these. Now, I cannot stress the importance enough of this. Like I said, understand that in this class, when we do something, it's not to be taken lightly, because in order to succeed, as farther along we go, you're going to have to stick with everything that we've just talked about. So there's none of this, just don't worry about that. Because if you just don't worry about that, okay, that's fine for your quiz. That's 30 points you lose. But you're also going to lose from here on out, because you're not going to know what any of these things are when we get into all these chemistry equations and stuff where we're going to be using them and happen to be able to name them. So it is very important that you stay on top of this. There's a bunch of other stuff. There's a couple other sections down here at the bottom of this. Ignore those. Okay? The only thing that you have to study for this quiz are these first two sections where it says polyatomic ions and prefixes. Now the prefixes should be easy. You should already know most of those anyways. So those should be 10 points that you do not miss on this quiz. The setup will be sort of the same as what you just saw in the element quiz. Half will be missing. Either the name, like there may be hexa and you have to fill in the 6, or there may be 9 and you have to fill in nana, one of the two. It's the same setup as the quiz you just had. Now up here is where it gets a little bit challenging. These are polyatomic ions. Ions are atoms with a charge. I want to discuss that in this lecture. But notice that, for example, the acetate ion. Acetate is C2H3O2 with a negative sign after it. If you don't put the negative sign, it's wrong. Okay, all of these things are going to have charges after them. Some of them will have a -3 charge, -2 charge, a +1 charge, whatever those are, they have to be included with the formula for this ion. Some of these you've heard of, some of them you've probably never heard of before. Like for example, peroxide is actually oxygen. You think of oxygen as O2, but when there's O2 and there's two oxygens stuck together and they form a -2 charge, that's not oxygen anymore. It's called peroxide. Okay. Yes, I don't care. It doesn't. You don't have to. It can be 2 positive, +2, as long as there's a positive sign and a 2 there. That's all I care about. Okay, and spelling has to be close again. Okay, some of you were way off on some of the spelling to the point where I didn't really know what you were saying. If that's the case, then I have to mark it wrong. But if you say, phosphate and you write phosphate and you forgot the H, I'm obviously going to know that you're okay. Okay. Now, as far as any tricks that go along with this, so you got to keep in mind, if you write CN and you write big, now these are not elements. So, for example, you can stick more than one thing together. CN is actually carbon and nitrogen stuck together to make an ion. We call that cyanide. Okay, this is a cyanide ion. If you write big C little n, it's wrong. Okay, that doesn't tell me the right thing. There is nothing that's represented by a little n. So you've got to keep this in mind. ClO2 means that there's chlorine and 2 oxygens stuck together to make this ion with a 1 negative charge. As far as hints, the only thing that I can really tell you at this point for you to understand, and I know this is, it's sort of just you have to memorize it up front and trust me with it and realize that you're going to be applying this as we go along. And some of this stuff about how they got their name and the reason they are the way they are, you'll learn. But for right now, we have to know how to use these. Just take it on faith and memorize these, and then I'll teach you why later. Okay? For example, look at these two, sulfate and sulfite. They are very similar. There's only one letter difference in their name. However, if you get them confused, it's wrong. Okay? Ate and ite. Generally, if you have ate or an ite, notice what all of these things have in them. There is one atom that is shared by virtually all of these, except for this one and this one. What atom is shared by all of them? Oxygen. Oxygen is the culprit, and that is the reason why these ions are existing, because of the properties that oxygen has. We'll discuss that a little bit later. But generally, they all end in ate or ite, if you look. Now, there's some difference every once in a while, not, but a lot of them end in ate and ite. That means there's going to be an oxygen involved in the formation of this ion. Generally, if you have two things that are very similar, like sulfate and sulfite, the ate is going to be the one with more oxygen. The ite is going to be the one with less oxygen. So sulfate is SO4, negative 2. Sulfite is SO3, negative 2. Look at, I don't know if I have phosphite on there. Maybe just, well, I have nitrate and nitrite. Okay? Nitrate is NO3. It's 3 oxygens. Nitrite is NO2, negative. Now, where it gets really kind of tricky is if you look at these guys here. Take a look at this one, this one, this one. Where's the other one? This one. Chlorate, chlorite, hypochlorite, perchlorate. How can you tell the difference between them? Well, if you look here, yes, all of them are ranked in terms of their oxygen. Okay, rank them from lowest to highest in terms of oxygen. You'll see that that's 1O, right? Cl1O, Cl2Os, Cl3Os, Cl4Os. If you rank them, pick the middle two as your ate and your ite. So of the middle two, whichever one of those has more, like here's your middle two, right? This is the 2 and the 3. You've got 1, 2, 3, and 4. Position them in order. Your middle two is going to be the 2 and the 3. Whichever one has more of those two is chlorate. Whichever one has fewer is chlorite. And what do you do with the other two? Well, this one has even fewer than chlorite. What does the prefix hypo mean? Less than or fewer than, right? So hypochlorite. This one has even more than chlorate. So instead of saying hyperchlorate, they just call it perchlorate. Okay? So think of that. That might help. There's at least 4 of them, and with the sulfate and sulfite and nitrate and nitrite, you can sort of get those. A lot of them you can sort of pick up some things. Obviously, hydrogen tends to actually be in the name of the things that have hydrogen in them. Not all the time, but sometimes. You'll have to sort of come up with your own schemes and how. There's some really dumb ones out there. I remember there was one lady taught high school who tried, it was dumb, but about how, like, how to memorize carbonate. It was something about, like, this is just going to confuse you, so you might want to just go la 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 while I'm saying this. But like, had like something about a C with ears, and it had like 2 ears when you put the 3 on it, or something like that. It was really stupid. But you can come up with all these ways that you can figure this out on your own. Whatever you need to do. But make flashcards, do on front and back, have someone go over those with you. You'll be thankful, because you're going to need these throughout the semester, I promise. So it needs to be to the point where when you see them, you recognize them. And even if you don't automatically know the name, you're thinking, oh, wait, this is a polyatomic ion. I knew that I had to memorize it. I can go back and look at it. You have to be able to recognize it. Because when we get into naming and chemical equations, it's going to screw you up completely if you can't keep these things straight. So I know there's a lot of them there. There's a bunch more than that. Okay, I promise that. But let's just stick with this and try to memorize as many of these as you can. Generally, people do well on the element quiz, and then I see a rapid decline in terms of being able to memorize a lot of these here. So let's just see how it goes. We're going to have this quiz on Friday before lab. All right, any questions about it? All right. Really, though, I mean, there's no surprises. If you're willing to put the time in and memorize this, then there's 30 points you can get. So it's a matter of how good you are and how hard you're willing to work for those 30 points. It's straight up for you, though. You know what to expect. So. All right, let's get on with it here. Chapter 4, I told you to bring your periodic table, so I hope you did. You're going to be making some notes on your periodic table as we go along here. And if you didn't, you might want to get your book and at least make some notes in your book. We left off with what is an AMU? What does it stand for? Do you remember? Atomic mass units. What is the weight of a proton in AMU? 1. What's the weight of a neutron? 1. What's the weight of an electron? 0. Okay. This is just an easier way for us to keep track of the mass of certain atoms because the actual masses are extremely small, as you can see up here. So it's going to be much easier if we can just assign an arbitrary value to this and use the same for all of them and calculate mass that way, just relative to each other. Okay. Now, let's get into the elements here. Remember, I mentioned this, but I'll mention it again. As far as elements go, what happened to the other table that we had in here? You guys want this table? Come here, help me carry this. There you go. Look at that service right there. Right up to you. Now, if you look at your periodic table, you see a lot of elements on there. Those are an example of all the types of atoms that are known to exist in our universe, at least that we've discovered. Now, what makes one element different from the other, besides their name, how do you get their name, is how many protons are in their nucleus. That is what defines hydrogen, for example, from lithium. Hydrogen has one proton. An atom with two protons is called helium. An atom with three protons is called lithium. So, we call this the atomic number. Now, if you look on your periodic table, if you printed off the one from the web that I had on my page, you will see that at the top, look at hydrogen, it's the very top left element, H. You will see that in the top left corner there's a number 1. That is the atomic number for hydrogen. That number tells you how many protons are in the nucleus of that atom. If you look at lithium, which is one down, it's number 3. In the top left, you'll see a number 3 right below hydrogen. What that tells you is that there are 3 protons in that nucleus of that type of atom. All right? Notice how your periodic table is arranged. As you read from left to right, and then you go down to the next line from left to right, and you keep going down, you will see that it is arranged in order of increasing atomic number. The atoms get larger, so at the bottom right of the table, and ignore those last very 2 rows for a second, kind of out there by themselves. Look at the big block at the top there. The bottom right, you will see, as farther down you go and the farther right you go, you will see the elements get bigger in terms of their atomic size, or in terms of their number of protons, sorry, in their nucleus. Okay, now, they all have a symbol. As you know, at least 30 or 31 of them you should already know. You'll get used to some other ones as well. If they have 2 letters in their symbol, it will always be an upper and a lowercase letter. Okay, so don't get that confused. So there's a lot that we can tell just from looking at a periodic table. I'm going to explain all of that now. But first, if you just take a look at the generic, so we said this was the atomic number, that small whole number that's going to be on there. They're generally the symbol. Sometimes you'll have the name, sometimes you won't. The one that I have on the web doesn't have the name, but some tables do. You're going to see one other number here that I'm going to talk about here in a second. It's called the atomic mass. It is not the atomic number, the atomic mass. The atomic mass comes from adding 2 things together. It comes from adding the protons and the neutrons, because that's what an atom's nucleus is, protons and neutrons. And I told you that the mass of electrons is negligible. So to get the atomic mass of something, you want to add up the protons and the neutrons. To just get the atomic number, you're looking at the number of protons only. So in this case, notice that hydrogen is about 1 for its atomic mass. Its atomic number is 1. What does that tell you about the nucleus of a hydrogen atom? It has no neutrons. It only has 1 proton. Take a look at helium. It has an atomic mass of 4, an atomic number of 2. What does that tell you? 2 neutrons, usually, and 2 protons. Now, you may ask yourself then, if you are a student who catches on to things very quickly, how is it possible to have 1.01 of a neutron or a proton? For example, if hydrogen atomic number is 1, and its atomic mass is 1, and we are assuming that its atomic mass is 1 because it only has 1 proton, how can it have 1.01 proton? How can sodium have 22.99 as a number? Either you got a proton or a neutron, or you don't, right? So where do these come from? I'm going to talk about that. I'm going to tell you why these are decimal numbers. A little thing called isotopes. Okay, we'll discuss those a little bit later. Okay, so here we go. What is the atomic? Don't look. What is the atomic number of boron? You look at your table. Don't look at the answer. You don't have to have the table memorized yet. No, you don't have to ever have it memorized. Don't worry. 5. Good. What is the atomic mass of silicon? The atomic mass. 28.09 on my table, right? Not the atomic number, the atomic mass. How many protons does a chlorine atom have? 17. Find chlorine. See, this is another exercise you're going to get very good at. When I say how many is this and you're looking at the table, your eyes are going to go there if they don't now. You'll find them. You'll get used to these things. It's in the next to last column, second from the top. Chlorine has what? How many protons? 17. Good. How many electrons does a neutral neon atom have? But before we start, what does that mean? That's right. It'll have to have the same number of electrons as it does protons to be neutral, right? So, 10. Right. It'll have 10. Will an atom with 6 protons, 6 neutrons, and 6 electrons be electrically neutral? Yes. There's 6 positives, there's 6 negatives. Those 6 neutrons don't matter. They don't have a charge in this case. And it's not going to play out. Will an atom with 27 protons, first of all, tell me what that atom would be. An atom with 27 protons. Cobalt. An atom with 27 protons, 32 neutrons, and 27 electrons be electrically neutral? Yes. Will a sodium atom with 10 electrons be electrically neutral? Why? How many protons does sodium have? 11. Right. So it's not going to be charge neutral. What do you think the charge is going to be? A positive 1. There's one difference between the electrons and the protons here. Okay, good. All right, here's where we're going to start labeling some things. Something called periodicity. It's called the periodic table of elements for a reason. There are certain repeating patterns that occur throughout it. It's more than just a simple splattering on the wall of a bunch of elements in some random numerical order. For example, why, when you start with hydrogen and then you go to helium, why is there that big gap between them? How do you know to only go 2 wide? Whenever you go down to the 4th row and you start with potassium and you end with krypton, how do you know that you end with krypton and jump down to the next row? Why is it organized that way? Why isn't there like 35 of them in a row all the way across? Well, we're going to talk about all the details of this. There's a lot of things involved. Okay? So first of all, let's break it down into 3 big groups. Everything on the periodic table can be one of 3 things. It can either be a metal, a metalloid, or a nonmetal. How do you know the difference? Find this area right here on your periodic table. It's called the stair step or the zigzag. It's going to start with this right here, which is what? Boron. Right underneath boron is where you would start to draw a zigzag line. Trace it just like you see here. Make it heavy and dark so you can see it. It's like giving the eye step. Please make your mark heavy and dark. When you are done with it, this section of the test, you may review your questions for this section only. Make your mark just like this all the way down. And the boxes on your table that correspond to those green boxes up here on the screen, unless you're red-green colorblind, then you've got a little bit of an issue. Let me know, and I'll point them out to you. Or have someone else next to you. The green ones, notice that all of them will straddle except for this top one, boron. Right below boron, we won't count. It should be what? Aluminum. Aluminum's a metal. You know that. Okay, so we won't include that. So here we go. All these guys right here are called metalloids. Okay? If they touch that stair step and they're not aluminum, they're metalloids. What does that mean? That means that they're going to act sort of in between of what a metal would act and a non-metal would act. They're sort of that transitional point between the two. You'll find things like silicon here. Silicon chips. The reason that we use them in technology and things like that is because they're called, you also heard the word semiconductors maybe. Semiconductors, metals are conductors of electricity, right? Metalloids are semiconductors. They conduct a little bit like a metal, but to the point where you can actually control the degree of their conduction, unlike metals, which makes them great for controlling electrical impulses and electrical movement of data and things like that. Okay? But anyways, you don't care about that. Just know that these are metalloids. Now, anything to the right of those guys, as you can see up here in red, those are all nonmetals. So label them accordingly. Everything to the right of that stair step, to the right of metalloids, are nonmetals. That leaves everything else except for hydrogen. Don't forget, hydrogen is red. You know that hydrogen is not a metal. It's over here, and I'll explain why it's over here a little bit later. Okay? It's stuck in here with the metals because it sort of behaves in a similar way, and it's organized atomically similar to metals, even though it is actually a nonmetal. So you've got metalloids, nonmetals plus hydrogen is a nonmetal. Then you got everything else. These are all metals. Everything else. So jot that down. Then we're going to start breaking it down into certain columns, certain sections. You can keep going down farther and farther. All right. What about metals? What makes a metal a metal? What do you think that is? Mercury. Mercury is the only metal that is liquid at room temperature. This is sodium. Sodium is very soft as a metal. It's not like those hard metals like iron, things like that. Sodium, you could take a butter knife if you had solid sodium and cut it. The only problem is it could actually react if it was humid enough in here and there was enough water vapor in the air. It could start combusting, and it could actually start reacting very violently, even with a little bit of water vapor. Sodium is very, very reactive. It does not stay in solid form hardly at all. And in nature, it doesn't exist in solid form. It's always reacted in terms of a little ion floating around and stuck with something else. Okay? But that would be elemental sodium. If we could make it, that would be made, isolated into purified elemental sodium. So metals are solid at room temperature with the exception of mercury. Remember the symbol for mercury is Hg. They tend to reflect light pretty well. They're shiny. They conduct heat very well. They conduct electricity very well. And they are malleable, so they can be shaped and bent and drawn out, all kinds of stuff. And they are ductile. They can be drawn out into wires. Okay, drawn or pulled into wires. So how is that? Come on, don't fight. You can lose what happens to metals is they tend to, in chemical reactions, lose their electrons and form what's called cations in reactions. Now I'm going to discuss this a little bit further, but what an ion is when an atom loses or gains electrons. Okay? If you have a sodium atom and it has atomic number of what? 11. If you have a sodium atom with atomic number of 11, if you had elemental sodium, that means it would be charged neutral and it would actually have 11 electrons. Okay, 11 protons, 11 electrons. However, if that sodium loses an electron, because what metals like to do, one of the reasons they're defined as metals is they like to lose electrons in chemical reactions. They would actually have an electron leave their orbit and go somewhere else. And when that happens, how does that change the count? Now you go from 11 protons and 11 electrons to 11 protons and 10 electrons. There's a positive 1 difference there. Okay? That would be an ion. An Na with a positive charge that's what happened to it. It lost an electron. It became an ion now. It's not an atom. It's an ion. So all an ion is some sort of charged atom. When those things are positively charged, we call them cations. When they are negatively charged, how do you think you get a negative charge? You gain an electron. If you had, for example, if that sodium was an 11 proton, 11 electron system, and it gained 1 and became 11 protons and 12 electrons, now you're 1 in the negative, right? 1 extra negative. If that doesn't happen with sodium, but if it did, then that would be called an anion. So a negative charge is an anion. Think of it like cats are good, ants are bad. So cat is positive, ant is negative, and so, yeah. There you go. That'll work too. Yeah, that's probably easier than what I have, right? So that's a good one. Cation has a cross in the middle of it for the T, so that's a positive sign. So there you go. All right. About 75% of all of the metals of all the elements that are out there are actually considered metals. Okay, so they take a big chunk of the periodic table. And they are to the left and down. So the farther left you go and the farther down you go, the more metallic the element becomes. I'll discuss more of that a little bit later. Anybody know what that might be? Yeah, that's molecular chlorine. That's gaseous chlorine, sort of a yellowish color. You ever notice how, like bleach, if you ever leave bleach out, it can actually sort of, you can see it sort of yellow if it's really strong bleach, or sometimes yellow fumes and that kind of stuff. We can discuss why and what chlorine is a little bit later, or sorry, what bleach is a little bit later. But there's definitely chlorine involved. It's an interesting point too that someone said. I think it was you that said it's very toxic. Sure, it's deadly. I mean, chlorine gas will kill you. It's interesting too because sodium metal is very dangerous as well, extremely dangerous. So you've got sodium metal that will explode sometimes in a humid enough environment. You've got chlorine, which is toxic and will kill you. You put it together and we eat it. Right? How is that possible? I'll explain that a little bit later as well. Okay. There's my teaser hanging out there. Yeah. All right. Nonmetals are found in all three states. Okay? Make a corny joke out of that, I suppose, but I'll pass. Found in all three states, meaning what? What do I mean by that? Solid, liquid, gas. Right. You're going to find nonmetals in all three states. They are poor conductors of heat. They're pretty much poor conductors of everything. Poor conductors of electricity. The solids are very brittle. Think about sulfur. Have you ever seen like solid sulfur or sulfur deposits or something like that? It's kind of brittle. It's not like metal at all. What they tend to do are gain electrons in chemical reactions. So it makes sense then that metals like to react with nonmetals because one likes to lose them, one likes to gain them, and it's like commercial. Like, you got what I need. So they come together. And magic happens. Your metals are going to be on the right side of the periodic table. Nonmetals on the right side of the periodic table. The farther to the right you go and the farther up you go, the more non-metalish it sort of becomes, if you can think of it like that. Except for hydrogen. It is a nonmetal and it's on the other side of the table. So keep that in mind. Metalloids. They show some properties of both. That's why they're sort of in the middle. They're also known as semiconductors. And I give you, like, for example, a silicon. We can use silicon for like computer chips and that kind of stuff. You can also, it's so diverse. You can also, make caulk out of it, silicone and putty and caulk, and because it's sort of semi-solid, other. Yes, you can use it for those too. And it's sort of unreactive in that sense as well. So, all right. Now, silicone and silicon are a little bit different. Silicone is a compound that's made from silicon. There's other things involved with that. Silica is also made of silica atoms, like glass and sand. Those are actual arrangements of silica atoms with other things involved. So, okay, it's very interesting too. We'll talk about when we get into we'll talk about carbon a little later when we get into chemical bonds, and you will see that carbon is very versatile in terms of the bonds that it can form. That's why there's a whole branch of chemistry called organic chemistry that studies carbon and the bonds that it can make. Silicon is very similar to in a lot of ways to carbon in terms of how it can bond to things. And a lot of scientists predict that if life exists as we know it, like how we define life, if life is like this somewhere else out there and it's not a carbon-based life form like we are, it could very likely be a silicon-based life form. Because of the properties that silicon has, it's sort of like carbon. I'll explain more of that a little bit later. Okay, you will find that when you have a column going down, like all the way to the left, for example, hydrogen, lithium, sodium, potassium, rubidium, etc., all the way down, you will see that these things are going to behave in a similar fashion. They're going to have some chemical properties and they're going to have some physical properties that are similar to one another. That's why they're in the same column. We call these columns, you might want to note this, groups or families. I'm going to call them groups. You'll see it both ways, but I think in this class mostly just groups. So up and down columns we call groups. So group 1 is like hydrogen, lithium, sodium, all those guys. Group 2 would be beryllium, magnesium, calcium. Group 3 and so on, all the way across. Now, they're designated by a number and a letter at the top. Now, depending on the type of table you have, I need you to understand this. If you have the one that you printed out from the web page, from my web page, you'll see that there are two different ways to write the group numbers. You may see one that just goes from 1 to 18 all the way across. From number 1 to number 18, straight across the top. So hydrogen, the first column is 1, the second column is 2, the third column is 3, and so on all the way across. You may also see a different way to write it, like 1A, 2A, 3A, or sorry, 1A, 2A, and then it goes to 3B, and then there's a big blank in the middle, and it goes for a while until you get back to A, back with boron, then you'll get back to 3A. Okay? Now, it doesn't really matter. It's just a matter of different people organize it different ways. You'll see why, as time goes on, that it's just a matter of how you want to break it up. Generally, well, I'll refer to both. Like, for example, if I want to talk about the columns all the way to the right, I might say group 18, or I might say group 8A. Okay, either one, it's the same. Because I'm going to stop referring to them by group numbers in a second, because I'm going to give each one a name. These guys are called noble gases, for example, all the way on the right-hand column. And I'll start using those names, and then you don't have to worry about those group numbers anymore. But just know how to find the group number if I ask you to find it, so where you're looking. Okay, rows are called periods. Okay, so as you go down from left to right, for example, the second period would start with lithium. You should see that on the one you printed off from my web page. There's numbers going down the side, 1 through 7. There should be a total of 7 periods. As you notice that, like hydrogen and helium make up one. And then there's only a few in the next one, starting with lithium, ending with neon. That's the second period, and so on and so forth all the way down. You will see, and later on, I think chapter 7 or something when we get into, you'll see why these periods are organized the way that they are. It has to do with electrons. Okay, so you're going to see repeating patterns over and over for all these things that are related, especially in your columns that you see, especially in these groups. All right. So we have, it says the main group elements are, if you look at the naming mechanism that says groups like something A, 1A, 2A, all the ones with A on them. All the or after them, like 3A, 4A. Anything with an A after it are called main group elements. What you will see on the periodic table is that, if I go back, I can get a table. You should see that the first two columns, over here on your left, the first two columns, starting with hydrogen going down, and the next one over, starting with beryllium going down, those are A, group 1A, group 2A, or group 1, group 2. Okay? Now, those guys are considered part of these main group elements. Then you'll see a big rectangle right in the middle of the table, right? It's the top of the rectangle starts in 3B. It starts with what is it, SC? Yeah, scandium is where it starts. It's atomic number 21, so you can find that. And if you can continue to go down now, 1, 2, 3 more periods, and you've got the side of a rectangle. Go all the way across and make a perfect rectangle, and you'll see all those ones I'm talking about. Those are not main group elements. Those are called, they're going to be what's called transition elements, because they represent a transition sort of from one side of the table to the other. And the reason that they're different is because when we get into like charges and predicting what they're going to do, they're a little bit more unpredictable. They're a little bit more, you don't know if they're going to give off this many electrons or this many electrons. It's hard to say sometimes. So since they're not as predictable, they're separated out. And notice that's where all the B terminology comes from. The something B and the something B. It's just that lump of that rectangle right in the middle. Those are called transition elements. Now what I want you to notice is, look at the very bottom two rows. They're labeled lanthanides and actinides. Okay, I'll go over the names of those again in a minute. But look at the bottom two rows that you see. Notice where they actually fit on the periodic table. They're down there because they're pulled out, because they screwed up the geometry of the table if they were included. Look where they actually go. See if you can figure it out. What is the number for the first one, LA? Okay, find where 57 would be on the table. And you'll see that there's a big gap between 56 and 72. That first row that you see, that starts with LA, the lanthanide row, the very top row at the very bottom. fits into that space, like where that one block would be. It's supposed to be wedged in there. All of those go between 56 and 72. See how that works? They all wedge in there. Likewise, right below that is where the next row is wedged into from the bottom. What we call the actinides, the very bottom row. You'll see that it starts with what? 89 and goes to 103. So that goes right in between 88 and 104, and that's in a similar space in period 7. Okay? They're just pulled out because if they're wedged in there, it throws off the proportion of the entire table, and it makes it not as geometrically and aesthetically pleasing. Okay? So they're pulled out a little bit. All right, so those are still considered transition metals because of where they're supposed to be. Okay, so keep that in mind. So we've got main group elements sort of splitting the uprights over here. Okay, splitting the uprights would be the transition elements right in the middle. The uprights would be, if you want to use that terminology, would be your main group elements on either side. Okay. Now keep in mind, I talked about these bottom rows. They're called, not only are they transition elements, but those lanthanides and actinides, the two little bottom rows at the bottom, they're even further called inner transition metals. They're actually inside the block that would normally be there. So as a group, they're just called inner transition metals. They are very rare earth elements. You don't see them very often. A lot of them have to be synthesized and actually made in the lab. They are very heavy. They're very big atoms, usually unstable. For example, this is where you're going to find polonium, plutonium, that kind of stuff. Those are going to be down there. Uranium. These are the heavy metals that are going to be down in this area. Okay. Now let's break it down even more. What are the different types of metals that exist? We know that these are metalloids. We know that these are nonmetals. We know that everything over here is metals except for hydrogen. We know that these actually go right in here. Okay? And these are all considered transitional elements. And these are all considered main group elements. That's what we know so far. So you should be able to identify all of those parts. Let's break it down, because there's different types of metals. There's different types of non-metals and that kind of thing. So take a look at the first group, Group 1, or Group 1A. Group 1 or Group 1A are called alkali earth metals. Take note, alkali earth metals. It's just easier if you sort of make note of this on your periodic table and you don't have to look through all these slides. You can just sort of study it all on your table. Alkali earth metals. The next one over are called I messed up. Don't do that. The first column is alkali metals. The second column is alkaline earth metals. My fault. I don't know what I said the very first time, but I didn't catch it. Alkali metals are like sodium, potassium, all those guys in Group 1. Alkaline earth metals is the second one over, where you have like beryllium, magnesium, calcium, and all those guys. Okay? So notice the difference in the naming. Alkali, alkaline earth. All the ones in the middle are called transition metals. We've sort of already alluded to that. They should already be, if you have the one printed off from my webpage, all these should already be colored for you. So that big, on mine that I printed off, it's a big blue block in the middle. That's the transition metals. Okay. Notice where it begins and where it ends. Make note of that. So far we've discussed 3 groups of metals. Questions about this before I go on? Just a matter of remembering. Not too bad. All right, now let's skip this section right here and go all the way to the end, because it's easiest to work our way towards the middle of the table. All the way at the end, we have what are called, it's hard to tell the difference between halogens and noble gases, but the darker one here is what we're going for. Noble gases. So helium, neon, argon, krypton, all those guys going down that very last column. Group 18 or Group 8A, depending on which classification scheme you want to look at. Those are all noble gases. Think of them sort of, we're going to talk about the properties of them, but sort of like nobility, are a little bit pretentious and maybe don't want to react with anybody and interact with anybody. Noble gases do the same thing. They do not like to react at all. So when you actually suck in helium from a balloon, it does not kill brain cells. Okay? unless you're, now at some level you could make an argument saying that since you are technically depriving the body of oxygen, it's possible that for a moment there are some cells become deficient for the lack of oxygen. But helium toxicity is not the problem. There's no reaction involving helium. It's just really annoying, so Mom said to stop it because you're killing brain cells. Okay? Helium is an inert. It's unreactive. So is xenon. If you want to have the opposite effect, you can actually inhale a bunch of xenon gas, and you would lower your voice tremendously as opposed to making it high pitched. Anybody know why? If helium and xenon, for example, are unreactive and they form no chemical reactions, how do you explain why it makes your voice change? It has to do with your vocal cords are certainly involved. Do what? Why? Because it's what? Because that makes it, keep going, you're exactly right. If something is lighter and something is heavier, tell me, yes. What will happen is helium is much lighter than air. It only weighs, what, 4 AMU. What is air? Oxygen, carbon dioxide, argon, nitrogen, a lot of stuff mixed in that's going to weigh a lot more than what helium would. So if you suck in helium and then you blow out helium, they're much smaller, so they're going to travel much faster. They're going to fly past your vocal cords much faster, cause them to vibrate much more quickly. Increased frequency and vibration of your vocal cords is what gives you a higher pitch. Whereas if you get something heavier like xenon that is heavier than the other elements of air, when you breathe it, it's going to move much slower than normal air would. So you would get a much longer vibration, much lower frequency in terms of your vocal cord moving, and it would be a much lower voice. Pretty cool. Just so you know, another way to do this is, and I'm not advocating this, but another way, I don't know if they've changed it now, I have to look at the ingredients, but you know those duster bottles that you spray on like for computers and stuff? There were some trace elements in that were inert, virtually unreactive, but allowed you to obtain a mass of matter that was heavier than air. So if you sucked in these dusters and sprayed it in, you can actually talk with a deeper voice. But the problem was with that, guess what mostly that stuff is? It's CO2. So what happened is you can get CO2 toxicity. You can get an adverse reaction to too much CO2 in your body. It shifts your equilibrium and your homeostasis to the point where you can get sick. Worst case scenario, you could die, but not probably just from sucking, unless you sucked a whole lot of that. But it can certainly make you sick, make you nauseous and that kind of stuff. So a lot of kids were finding out you could suck this pressurized container and talk a lot lower, and it was cooler, but you're also putting a whole lot of CO2, which is not inert, and it is reactive. I have a problem with that. So, anyways, next time you're at Walmart, you're thinking, I got to get me some of this, get me some of this. All right. Let's move one more in. Next column in. We call these guys the halogens. You've heard of like halogen lamps, stuff like that. We can discuss that a little bit later. Halogens are your chlorine, your fluorine, your bromine, your iodine. These are all guys called halogens. They are very reactive species. They like to, these guys are completely unreactive, but once you get here, you become very reactive, and then you diminish in terms of reactivity the farther towards the center that you get. Okay? But these guys are very reactive. They're almost, I'll explain a little bit later as to why, but it has to do with the fact that they're so close to these guys. This represents like a nirvana in chemistry, these noble gases. They represent the place where everyone wants to be. So because these guys are so close, they are very reactive in an attempt to get there. And because these guys are only one in the other direction, they just got to fall back one, right? These alkali metals, they just got to fall back one to get to the previous noble gas. They're so close, that's why they're so reactive. Okay? And I'll explain all that a little bit later. All right, so we've got alkali metals, alkaline earth metals, transition metals. So all of these are metals. We've got nonmetals, we've got metalloids. Also nonmetal is hydrogen. We already said those, so we're at noble gases, halogens. Okay? These guys are part of the transition metals up here, but they will have a special name. And here we go. The actinides are the ones on the bottom, and lanthanides are on top, actinides are on bottom. They should already be labeled on the one that I have on the web page, but you'll have to label it if you don't have that one. So, let's go back. and you fill it in. Okay? Tell me, what are these guys called right here? Noble gases. What are these guys called? Lanthanides. What's all this called? Okay, what are these guys called? Halogens. Good. What are these guys called? Okay, altogether they're intertransition metals, but of the two types of intertransition metals, we've got anthonides and lactanides down here. What is this group right here called? Alkaline earth metals. What are these guys called? Alkali metals. Okay, there you go. See? You're ready for the test. At least a couple questions on it. Hang on a sec, I see you. Okay, move on. There we go. Question? Good question. Let me point out something here. And I don't know if I get to it soon, but I'll go ahead and say it now. No. Well, let me explain why. Zinc, well, no, there's too much stuff that's implied that I have. Where do I start to explain? But look at zinc, find it, it's number 30. Look at zinc, go ahead and draw this. Find zinc and cadmium, which is right below zinc, and then just to the left of cadmium you'll see silver, right? Okay, trace those all in, all three of those. Trace them all in, form a little boot. I call it the boot. Okay. Now, you're going to find, and I'm going to explain the charges of all this stuff a little bit later, but those three right there, and I'll show you some more a little bit in a minute. The reason that we're not going to consider them transition metals, because they're not, because the reason is because, as you'll see in a minute, transition metals form different charges depending upon the circumstances. For example, iron may form a 2 positive, 3 positive, or 4 positive charge. It just depends. But what you'll find is all these groups that we just talked about, like alkali metals, alkaline earth metals, halogens, they all form a predictable charge on the table. They all form the same charge every single time. What you will find is that zinc and cadmium, they both form a constant charge. So they're not going to be a transitional metal. Okay, they're considered a metal, but they're not really a transitional metal because they can form one relatively constant charge. You'll find that mercury, however, just below that, does actually flip back and forth between a couple charges. So it's real tricky. There's not a fine line there. You could probably throw mercury in over with the transitional elements, but not zinc and cadmium. So I just left those out entirely on this block. If you look at silver, this is kind of odd too because silver is in the transitional element place to where you would think it would form multiple charges, but it does not. Silver usually only forms one charge. It's a 1 positive that it forms, and I'll explain that a little bit later. So it's kind of hard to answer that question, okay, because it depends on how you look at it, really. All right, let's look at hydrogen. I told you it was a nonmetal. It's colorless. It's a diatomic gas. What does di mean? 2. So what this means is when it exists as an element, if you have pure hydrogen, you will never have individual hydrogen atoms just floating around in a pure sample of hydrogen. What you will have is H2 molecules floating around. It's diatomic. It likes to stick to something, and if there's nothing else to stick with, it will stick with itself. Okay, so hydrogen is diatomic. It's colorless. It's very low melting point. That means to turn it from a solid into a liquid, it doesn't require a very high temperature at all. As a matter of fact, it's extremely low. Even in the universe, hydrogen exists as a gas. Okay, so it's very hard to get liquid hydrogen, much less solid hydrogen. I mean, it's a ridiculously low temperature would have to be achieved to do that. It has a very low density. Remember, density is the ratio of its mass to its volume. How much matter is packed into a given space. It's very low. Hydrogen is very small, and there's a big gap between neighboring hydrogen atoms virtually in any sample that you have. So they have a lot of space in between them. So it's a very low density. They like to react with nonmetals to form molecular compounds. For example, H and Cl. Chlorine is a what? Halogen. Good. Chlorine is a halogen. It is very reactive. I told you those halogens are only 1 space away from being a noble gas. That means they're very reactive. Hydrogen is also only 1 space away from that far column. What you will find is that hydrogen and anything in the same group as hydrogen, but hydrogen and halogens like to come together. They like to react with one another, and when you do, you get things like this, which is hydrochloric acid or muriatic acid if you go to Lowe's and buy it. It's an acidic gas. It can also be in an aqueous solution, but we'll talk more about that later too. H2O is a liquid, right? You have oxygen, you have hydrogen, very different from water, but when they come together, they form water, which we use. Oxygen is very reactive. Hydrogen is combustible. You put the two together, you could make an explosion. But it's another way they could come together is to make water, and then we can drink that. It's one of the most important molecules to us as life forms. Sometimes hydrogens can react with metals, though, to form compounds called hydrides. So a metal atom, a metal ion, and a hydrogen atom or ion can come together and form a compound between those two. We call those metal hydrides. When that happens, you get a rapid release of whenever you take a metal hydride, like sodium hydride or something like that, sodium that is reacted with hydrogen, and you have this compound now, it can react very violently with water, and it releases that hydrogen back out again in the form of diatomic hydrogen. It's two hydrogens stuck together. It's a very violent reaction. Okay. Anytime hydrogen is bonded with something, like Cl or I or Br or anything like that, especially a nonmetal, okay? It has to be in this case a nonmetal. When it is, the X is just generic. When hydrogen is bonded to something, it can dissolve in water. It dissolves in water pretty easily when you stick it in water. And when it does, now you've created an acid. That's what an acid is. An acid is something that involves the bonding of hydrogen that when you put it in water, now those things separated and they dissolved. And now you've got hydrogen ions that are floating around and are very dangerous. And they can react with a lot of things. That's what makes an acid an acid. We'll talk about that later too. Okay, now these are linked, so if you want to go on the web and read about each of these, then I guess I would say you could probably find something better to do. But if you want to read those, there's certainly a link to them. They'll just give you more about their size and maybe discoveries and things like that. But the alkali metals, there they are. Lithium, sodium, potassium, rubidium, cesium. Hydrogen is located above them, but it's not a metal, so it doesn't really belong to these guys. They're very soft. They have very low melting points. It's very easy to melt them, turn them into a liquid. They have very low density for a metal. That's why they're not very good for structural things. You don't build sodium buildings. Not only is it extremely reactive, a good rain would just blow up everybody. But in addition to that, they're not very sturdy. You'll be doing this, something called flame tests. They're kind of neat. I'll do a demonstration as well, and you'll be able to do some of your own stuff in lab. But metals, based upon the number of electrons they have, they give off a different color when they're heated. This explains why fireworks work. Like for example, whenever we're done with our unit, when we learn about all this, you're going to go to the fireworks the 4th of July, and you're going to look at it in a whole different light. Instead of saying, oh, that was pretty green, you're going to say, oh, copper, oh, sulfur, oh, magnesium. And you're going to be able to remember this, and you're going to watch it like I do, and then everyone's going to make fun of you, and then I feel better. Okay? Okay, for example, if you do a flame test on lithium, dip it in dissolve the lithium, you'll find that these metals dissolve in water very easily. Okay? Whenever they dissolve in water, it's very, very difficult to get solid sodium. It's very difficult to find solid lithium. But you can make it in industry. But if you had it dissolved in water, like say you had like a lithium chloride salt or sodium chloride, you eat that, right? And you dissolve it in water, you know that these things dissolve. But there are metal ions in there. There are sodium ions in there. If you can dip it in there and hold it in a flame and let them absorb energy, you'll see that they glow a certain color. Okay? Sodium's not all that exciting. It's sort of a yellowish color, so it sort of blends in with the flame and you don't really see it. But if you can get some lithium chloride, it's sort of like a bright, hot pink. It's really cool. Copper is like a real bright green color, and potassium is like a violet color, almost a whitish violet color. Pretty neat stuff. I'll explain all of that later too. Very reactive. They tend to form water-soluble compounds. In other words, they tend to make things that dissolve in water, like salt. And they don't have any color to their solutions, usually. Copper chloride may have a little bit of a color to its solution, sort of a greenish-bluish twinge to it. Let's see. And also, just so you know, if you can ever get a hold of some of this elemental stuff, if you take a lump of sodium, like if you had like one the size of a stick of margarine, for example, first of all, I don't know how you can hold it or anything. You'd start reacting with the water in your skin. But say you could grab onto it, and you went over to a bridge, went over to the Wabash River going across there to West Terre Haute, and threw this thing down in the water. Here's what you would see happen. Okay, this equation down here. So I'll teach you about balancing equations and all that stuff later, but realize what this means. Sodium metal is reacting with water. That's what this equation means. What do you get when sodium metal reacts with water? You get the right side of the equation. Sodium hydroxide, which is sort of like Drano, okay, and hydrogen gas. Also, a ton of heat. So here's what would happen. If you had this is very reactive. So if you had a lump of this soft metal and you dropped it in this water, all in fractions of a second, what you're going to get is the evolution of hydrogen gas. Immediately it's going to be released, and guess what gas does? It rises, right? So this is all this bubbling explosion that you're going to see is this huge rapid release of hydrogen gas. Not only that, but you're going to have a large amount of energy that is released. There's going to be a lot of heat released. So all that heat is going to heat up all the molecules that are around it and turn it even more into gas and heat them up to the point where it's going to just sort of explode when it does this. Okay, so it's pretty cool. Yeah, until you have to justify how you got elemental sodium, because you can't buy it anymore. There was a jar of it. Janine had a jar. Well, I used to teach high school when I taught chemistry. The lady before me had gotten, I don't know where she got it. She got some elemental sodium. She had to keep it you don't keep it in water, okay? You keep it in like a glycerin, alcohol type solution that it doesn't react with. But they used to sell it, and high school teachers could buy it and things like that. And now you can't buy it out of the catalog like that anymore. If I wanted to buy elemental sodium, I'm not sure how I would go about doing it. I mean, I could do it if I wanted to, but I'd have to probably fill out some papers and that kind of stuff. I bought uranium well, not uranium, like weapons-grade uranium. I bought a compound that contained uranium a couple semesters ago, and I had to fill out some paperwork for that, naturally. So just trust me, I guess. I don't know what I'm cooking up down here. All right. Moving in, Group 2A, alkaline earth metals. Little bit. You're starting to get a little bit more into what you think metals, what you normally would think that metals are. Okay, a little harder. Still pretty soft. Still not as hard as what you think of as metals are. They are harder. They're higher melting. They're denser. Anybody know what this? Well, I guess it tells you. Magnesium. Okay. If you're going to do a lab where you'll get to ignite some magnesium. It's very bright. If you've never seen it burn before, you could take a little ribbon of it like that. It's pretty soft. You can stick it in a flame to heat it up. Realize you're not really burning it like a fuel, but you're heating enough energy to start a reaction to where it sort of just passes that energy on to neighboring atoms, and they start reacting with oxygen from the air and forms little white powder on this called magnesium oxide. Okay, and it's really, really bright. It burns really, really, really bright. Actually, you remember those old-time like westerns that had like the guy holding the camera and he had that big flash pan out here to the side? That was actually powdered magnesium that was in that to provide that bright flash. It can, yeah, because as long as you get it hot enough, because what you're dealing with is not, you don't need oxygen. It's not a matter of supplying oxygen to it. It's a matter of heating it up far enough to start it reacting with even pockets of oxygen and water, even oxygen from the water around it. So yeah, you can get it started. You do flame tests on these guys too. There's calcium. If you drop calcium in water, now this we will do in lab, because it's not going to explode. It'll react violently and it'll sort of bubble up a lot. Not real violently. It'll bubble up a lot, but it won't be anything like dumping sodium in water. So you'll get to do that. You can see that it's far to a lesser degree of bubbling, but it's still kind of cool. Flame test for calcium, red. Strontium's red. Barium's sort of a yellowish green, so you'll get to see all these as well. The reactive, but not as reactive, the alkali metals. They form oxides very easily. That's how you usually extract them. Oxides, they like to react with oxygen. They tend to form like those white powders when they start reacting with oxygen, just from the air even sometimes. Oxides are basic in nature, meaning the opposite of acidic. Okay, I'll discuss all that later, but that's how they got their name. Alkali metals and alkaline earth metals, because they like to form things that are opposites of acids. So that's, alkaline means that. It's the same thing as basic, and alkaline and basic are synonymous. They like to react with water to form hydrogen like you see over here. Those little bubbles that you see are escaping hydrogen gas. Okay, now skipping all the way over to the next to last column, group 17 or group 7A. The halogens, starting with fluorine, moving down all the way. Notice that, for example, iodine can be a solid at room temperature. You can dissolve it if you'd like, but it's a solid at room temperature. Bromine is actually a liquid at room temperature. Chlorine and fluorine are gases at room temperature. So these are halogens. These are very reactive. They are all diatomic. They all like to react with themselves if there's nothing else present. So if you just have samples of, for example, if you have solid sodium, and you could look at all the atoms that were in that lump of sodium, what you would see is a whole bunch of individual atoms of sodium, all stuck to each other. They're just in there. They're not necessarily bonded with one another. I mean, I know that seems weird, but I'll explain that hopefully at some point as well. But these guys, what these guys do are, if you have a sample like this whole gaseous tube, if you could look inside this tube and look at the atoms that were in there, you would see that all the atoms are in pairs. They're all partnered up. And each one has a partner of them. They're the same. I mean, there's two chlorines stuck together. Or there would be two bromines in the case of that liquid. Or in this case, the units there are a bunch of repeating two iodines stuck together. Now, these two iodines and these two iodines can sort of stick together, and that's how you get this solid formation. Chlorine and bromine react very slowly with water. But when they do, they can form acidic type of situations. Bromine water is nasty stuff. Chlorine water is basically bleach. Bleach is diluted chlorine water, so it's nasty too. But bromine water, I don't even think they sell it now. In terms of, you can't just order it. Like if I order it from a catalog, I can't order bromine water. I have to mix it myself. I've got to get some of my own and figure out a couple reactions to sort of mix it together to make bromine water, because it's very reactive, it's very corrosive, very dangerous. They tend to react with metals to form what's called ionic compounds, meaning two ions come together to form a compound. Like Na, if it's positively charged, will come together with a Cl that is negatively charged and make an ionic compound. Two ions come together to make a compound. So this is where you're going to get a lot of acids too. Hydrofluoric acid is H and an F. Hydrochloric acid, HCl. HBr is hydrobromic acid, and we'll learn about how naming all those a little bit later. Noble gases are virtually unreactive. I already said this. It's funny because you think of neon signs and you think of the element neon, but there's actually a lot of other elements that you can use besides just neon. You can use any of those noble gases to make different colors. Actually, fluorescent lighting utilizes, notice that the color of light is a little bit different, right, on a fluorescent light than it is like an incandescent light bulb that you just flip on. It's because the color that you see here is actually due to a noble gas. That is, like when you do a flame test and it releases a certain color, well, if you supply an electrical current as opposed to a flame, it does the same thing. It causes these atoms to release a certain color, a certain wavelength of light. It just so happens that argon emits a whitish color of light. So that's the reason that the color is a little bit different. It's not like it's just glowing hot like a normal light bulb would be and giving off white heat energy. It's instead giving off a certain wavelength of light that's a little bit different than pure white light, but it's close. So there's a little bit of a subtle color difference. But what happens is those argon atoms absorb some energy that's in that. You ever take one of these break? They're gas filled, right? They can explode, they can break, and they can pop. The gas is in there. There's other things in there. We'll talk about that in the chapter when I talk about electrons. But argon atoms are absorbing some of this energy that you're circuiting through them. And when they do, they release it. They absorb a certain amount of it, and they re-release it in the form of light. And that's how come they can last so much longer. They're more energy efficient. It's not heat. When you take a light bulb and you turn on a switch to a light bulb, the reason that you're losing a ton of energy in the form of heat, because all you have is this little wire in there, and you're making this little place where the electricity jumps across from one place to another through that wire. And as it's exposed, it releases a ton of heat. So it's very inefficient. You're wasting a lot of energy. With these guys, it's all sealed up, and all that energy is being absorbed by those atoms and re-released, and they just keep passing it around, and it's not heat energy that's traveling through them. It's a little bit different. It's just using electrons to bounce around inside them, so it's much more efficient. Anyways, these guys are all gases, and they're very low melting points, very low boiling points. It's very, very hard to get them in liquid and solid form. Okay, they're virtually always gases. They don't react with anything, practically inert. It is very, very hard to actually nudge them to the point where they can lose an electron or force them to take an electron. That's why they're unreactive. You will see that the reason things react is because of their electrons. So if they hold tight to their electrons, it's very difficult for them to get them to react. Okay. I told you this already, right? The number of protons is what determines what the atom is. This can never change. If you try to change the number, if you take a hydrogen and you try to cram into it another proton, you can't. Unless you're planning on doing some nuclear fusion. Okay? That's what our sun does. It'll take that hydrogen gas, cram it together at high temperatures and high pressure, and form bigger elements, actually form more elements. We cannot do that. You cannot start changing, but realize that if our sun does that, when it takes a helium and just it crams together under these immensely hot and high pressure situations, when that happens, it's no longer hydrogen. Now it's a helium. You've taken two hydrogens, crammed them together, made a nucleus of two protons. Now you've got helium. So by definition, anytime the number of protons change, you have a new element. So it cannot change. Now, when we have radioactive and nuclear changes, I don't think we'll get to that, but if you take Chem 2, and I discuss radiochemistry and nuclear chemistry at length, but when radioactive decay happens, nuclei actually can start to deteriorate. Neutrons and protons can start to fall apart into little fragments, and that's like radiation that can be given off in the form of energy from that. Now, when that happens, you can actually get an element to sort of go backward. You can change the number of protons, and you know that this whole set of events sort of goes out the window. It's a little bit different type of chemistry there. Okay, so atoms that are electrically charged, we said those are called ions. And we said there was cations and anions. Cations are positively charged, anions are negatively charged. So to get the total charge, you're going to take the number of protons minus the number of electrons. Whatever that difference is your charge for that atom. So I already said, cations, anions. Okay. I told you that metals like to form cations. They like to form positively charged things. So to do that, make sure you're with me. To form to form a cation, what do you have to do in terms of your electrons? Do you have to gain electrons or lose electrons? Well, we're all over the place. Which one is it? You have to lose. If you gain electrons, you become more negative. If you lose electrons, you become, by default, more positive. Okay? All right. So, take a sodium atom. 11 protons and 11 electrons. Now, for a sodium ion, you would have 11 protons and 10 electrons. For a calcium atom, 20 protons, 20 electrons. Calcium ion, 20 protons, has to be because it's calcium, but it would only have 18 electrons. So it's a 2 positive charge. Okay? So the way that you name these ions is you just name them the same as you would if you were naming the metal. So for example, if you see this is sodium, right? If sodium loses an electron and becomes Na positive instead of just Na charged neutral, we still just call this sodium, but we write ion after it saying it's a sodium ion. Okay, so sodium ion, sodium. Calcium, same way. Okay, we just name this after the element itself. So calcium ion. This is important, so make sure you're paying attention here. Rub your eyes a little bit. Okay, wake up for this one. Mark this on your table. Group 1A. What you're going to see is these charges and these ions that form, you can predict some of these based upon the periodic table. If you look at group 1, hydrogen down, right? All of those guys like to form a positive 1 charge. So note that. Like at the top or the bottom of that column, somewhere where you can see it, they like to form a positive 1 charge. Guess what group 2A likes to form? 2 positive charge. Calcium likes to form a 2 positive. Magnesium likes to form a 2 positive. Now, you'll notice that once you get to the next one over, you start transition metals. Those are unpredictable in terms of their charges, so we're going to leave those blank for now. Okay? Now, what I do want you to notice are these 3 elements right here. They're towards the right side of the table on the other side of the transitional block. Okay? Find those 3, box them in, and note that they actually form a 3 positive charge. Aluminum starts with 13. You should see that they're all right below each other. Aluminum, germanium, right below each other, and ions right below that. They're in the same column. Box those in and realize that they form, make a note, a 3 positive charge. So we should have alkali metals, 1 positive. Alkaline earth metals, 2 positive. Aluminum, germanium, down. Well, at least those 3, the ones listed on here, a 3 positive charge. Now there's one more. I want you to go ahead, and I had you box in zinc, cadmium, and silver. For zinc and cadmium, write 2 positive. For silver, write 1 positive. So I should now be able to ask you the charges of a lot of these things on the table, and you should be able to know what charge they like to form. You don't have to know why or how yet, just know that they do. So if I had a chlorine atom, or chlorine ion, okay, what would its charge be? Chlorine. Did I tell you that one yet? No. Oh, well, never mind then. Sodium. Positive 1. Calcium. Well, that's too easy. Strontium. That should be on there. Plus 2, right? Positive 2. I guess I haven't given you the negatives yet, so we're moving on. Nonmetals. So in the case of, let's look down here, fluorine. Normally fluorine would have, it should be atomic number 9, right? It should have 9 protons and 9 electrons if it was charged neutral. Well, a fluoride ion actually has 10 electrons, making it a 1 negative charge. Okay? What you will see is that chlorine does the same thing, as does bromine, as does iodine. So what charge then can we put above all the halogens? Negative 1. Look at phosphorus. It likes to form a 3 negative charge. So it goes from having 15 electrons, because it had an atomic number of 15, so if it's a balanced atom, it would have 15 electrons, 15 protons. To become a 3 negative, it had to have gained 3 electrons to do that. That gives it a 3 negative charge. Okay? Oh, yeah, you see how that works. You'll see a pattern. What you should notice is a pattern as we go across the table. Okay? The way that we name anions is a little bit different. So instead of saying a chlorine ion, you would drop the "ene" and add an "ide" instead. Okay? So instead of fluorine, when it gains an electron and becomes an ion, we call it fluoride ion. Oxygen becomes oxide when it's an anion. Find group 7A, which are the halogens. And I told you, and you already told me, it's 1 negative. Look at group 6A, the next one in, with oxygen and those guys. Negative 2. Okay? Now for 5A, you can put that nitrogen and phosphorus have a 3 negative. That's okay. Don't go below that, because once you get into metalloids, that don't count. Okay? You got to stay with the nonmetals here. So, when you go from nitrogen to phosphorus, when you get to arsenic, realize that number 33, arsenic, is a metalloid, so you can't put its charges in with these. But for carbon, notice that would be 4, right? My question is this. Based upon your previous studies in the 1 chapter of chemistry and your other classes, What magic number sticks out in your head that makes things happy? They have how many electrons in their valence shell? 8. Let me ask you this. What's the difference between 4 positive and 4 negative, or is there? When you're trying to get to 8. Either 0 or 8. That's your midpoint. There isn't one. It's exactly halfway in between, right? So the carbon is extremely versatile. Notice there are only 2 elements on the entire table that could have a positive or negative 4 as their answer. Guess what they are? Carbon and silicon. I already mentioned silicon. Okay? What you will see is atoms are going to attempt to react in such a manner that they will either drop some of their electrons, go one way, to try to get towards a noble gas, or they will gain. Notice that if you are carbon with 4 electrons, I'll explain all that later, it doesn't matter which way you go. So you're very versatile in that respect. So know all those charges. Before you take off, wait, take a look. We said our alkali metals, positive 1. Alkaline earth, positive 2. We don't know these yet. We have to deduce that. I'm going to show you how to deduce those. These guys right here, 3 positive. Okay? Ignore this. Ignore this. These guys, 1 negative, 2 negative. What do you notice about this? Nothing. They don't have a charge. They don't form ions. They don't react. Okay? Don't forget about your quiz on Friday. So.